Hello and welcome. This video is about flux across a curve in the plane. It's very similar to line integrals of a vector field along a curve. We're now doing a vector field going across the curve. Okay. Now, this was the along the curve, the integral over the curve of f dotted with dr. And we did that both in 2D and 3D. Formulas were very much the same. For this discussion, we will be doing only 2D because we're going to be doing, well, the 3D equivalent is not with curves, it's with surfaces. So we're just sticking with 2D right now. Okay. So the line integral of a vector field along a curve was the integral of f dr, which we started off with the integral of f dotted with the unit tangent vector ds. That's the way we initially thought of it, that we're getting the tangential component of the vector field in the direction of the curve and then multiplying by a little bit of arc length and then integrating that. Right? That's the tangential part. We now want to look at the normal part. So rather than dotting f with t, we're going to be dotting f with n, the normal vector, the unit normal vector. So f dotted with the unit normal vector is going to be the part of the vector field which is perpendicular to the direction of the curve. Right? So it's the normal part of the vector field. And then we say across the curve as opposed to along the curve. Right? And this is often called the flux. Right? It's the sum of all the normal components to the curve, normal components of the vector field to the curve times a little bit of arc length. Okay, so let's set this up. Suppose we got the curve parameterized. R of t is x of t comma y of t. And the derivative would be r prime of t, y prime of t. Now this is a tangent vector, right? It's in the direction of the curve. And so we want to now find a vector that's perpendicular to that to be the normal vector. And if you think about it in the plane, what you want to do is just wherever your tangent vector is, you just want to rotate it 90 degrees. Well, you could rotate it clockwise 90 degrees, or you could rotate it counterclockwise 90 degrees. And what we're doing is we're rotating it clockwise, right? In the sense that if I'm walking along a curve here, and so my nose is pointing in the direction of the tangent vector, right? That's the direction I'm going. I can hold out my two arms, one here to my right and one here to my left, and sort of arbitrarily the choice is made. Now, there's some reasons, but it is still somewhat arbitrary. We're going to choose the right hand. So from straight forward, from my tangent vector, I'm rotating, looking down on it here, I'm rotating clockwise. Okay. So let's see if I can do this. So if I have my tangent vector here, so this would be r prime, then the normal vector would be rotated down to here. Right? And I'm using a lowercase n, not a capital N, for a reason which I will discuss momentarily. Okay. So here's the two choices. In the plane, it's really pretty easy to get a vector perpendicular to one you've already got. You just swap the coordinates and make one of them the opposite sign from what it used to be. So I'd have y prime minus x prime, that is swapping those two coordinates, or I could have minus y prime x prime. And we choose the first one here. This is the one that would be rotated in the clockwise direction. And the way I see that is, the thing about it is, if I've got a vector with both positive x and positive y coordinates, right, and I rotate this clockwise, the x component still needs to be positive, but the y component needs to be negative. So if x and y were both positive to begin with, then this is still positive and the negative ends up on the y component, right? So this one is the one that I want, and that's going to be my normal vector. That's not a unit normal vector. That's a vector exactly the same length as the tangent vector, r prime. So now I'm going to need to normalize it, make it a unit vector. I said it's funny as I say that, normalize it. Normalize it usually means making it a unit vector, but the word normal is meaning perpendicular. Normal is used way too often to mean too many different things. The thing I do want to note here, though, is that the length of this vector n is exactly the same as the length of r prime, right? You got r prime up here. You're going to square the two components, add them up, take the square root. Down here, you're going to square the two components, add them up, take the square root. But the negative sign is going to go away here, the minus x prime, because minus x prime times minus x prime is going to be positive x prime squared. So the length of that normal vector is the same as the length of r prime. Okay, so when we make a unit vector out of that lowercase n vector to get capital N, my unit normal vector, I'm just going to divide by its length. So now I'm ready to take a look at what this flux integral is. Okay, and so I want to do as I did with the tangential component. That is, I first find the normal component of the vector field across the curve and multiply that by a little bit of arc length. Okay, and then add it all up, so integrate it all. Changing some of the things here, some of the expressions to what they're equal to. Capital N is little n over the length of little n, and ds is the length of r prime times dt. Now we just noticed up above here that the length of little n and the length of r prime are the same, so those two cancel out, leaving just the integral of f dotted with lowercase n dt to be the flux integral here. Okay, now I'm going to do a little bit more to this. If I know that the vector field of xy can be written as the vector p of xy comma q of xy, so p and q are the x and y components of the vector field, then this f dotted with n, which we've already rewritten as f dotted with little n dt, can be written this way. The p and the q are both functions of x and y, but I'm just choosing not to write that at the moment. So I've got the vector pq dotted with little n, which is y prime comma negative x prime dt. And when you take that dot product, you get p dotted with y prime, and you get q dotted with x prime, and this integral is dt. And if you think about distributing essentially the dt into both of those parts, then the y prime dt is just dy, and the x prime dt is just dx. So this integral, this flux integral, which could be written this way, f dotted with capital N ds, or this way, f dotted with little n dt, can also be written this way, the integral of p dy minus q dx, although quite often you will see it written as minus q dx plus p dy. Okay, these can be written in either order because addition is commutative. Just a quick comparison of the formulas. The stuff we were doing before, integrating the tangential component, looked like f dotted with capital T ds, where flux integral now is f dotted with n ds. We converted the tangential one into f dotted with r prime dt, but this is now f dotted with little n dt, and likewise the tangential component written in this last form was the integral of p dx plus q dy, and now we have p dy minus q d, sorry, p, there's a typo there. Let's see if we can fix that. And yes, I do have the power to correct that. It's q dx. There we go. Let's do one example, calculation of a flux integral. I'm going to use the same example that I did a line integral of, the line integral of the vector field before. This is, the vector field is minus y comma x, so it's these in circular motion around the origin, where the stuff in the middle is moving slowly and the stuff on the outside is moving fast. And the curve that I chose before, and I'm choosing the same one now, is this circle here of radius 1 centered at 2, 0. So the parameterization I'm choosing is 2 plus cos t for the x-coordinate and sine t for the y-coordinate. essentially with t equals 0 to 2 pi. So at 0, you're out here at the rightmost point, and then you circle that thing in the counterclockwise direction. Okay. And actually, that reminds me, we had that choice of the normal vector one way or the other. And what the choice did for us actually is going to come up in later sections as we do a lot of different things with these curves that actually start and end in the same place like this one does. So it encloses a region. The orientation that we want for the curve quite often, what we call the positive orientation, is the one where as you're moving along it, the interior of the region is to your inside, and our choice of normal vector would be the exterior normal vector. Okay, so that would be the one as I'm moving counterclockwise here, off to my right is the exterior normal vector, and that's the choice that we made here. So using this vector field and this curve, I take the derivative r prime here to get my tangent vector. It's not a unit tangent vector, but actually in this case it happens to be just because coincidence. But that's the derivative here was minus sine, and that's cosine. And then I flop them and change the sign of this one to get the unit normal vector being cos t comma sine t. Sorry, it didn't happen. It is a unit vector, but it didn't. That was lucky, right? This is just the normal vector, which circumstances make it unit here. So let's calculate the flux integral, f dotted with n dt. So f is minus x comma y. I'm grabbing that from up here. And then n is that thing that I just had there, times dt. Replacing the y and the x here from the coordinates of the parameterization, right? Because we're not doing just every x and y, we're doing just the ones on the curve. So for different values of t, I'm getting different points on the curve. So the y component there was sine t, and the x component is 2 plus cos t. Now I can take that dot product to get the cos t times the negative sine t is that, then plus the sine t times 2 plus cos t, so I got 2 sine t plus cos t sine t. The minus cos t sine t and the plus cos t sine t are going to go away, and I've got the integral from 0 to 2 pi of 2 sine t, and this is equal to 0. You can either do the integral, or personally I look at the picture and I say, hey, I've got a sine of 2t, which looks like this. From 0 to 2 pi, there's just as much positive area as negative area, and I get 0. Okay. Could I have maybe foreseen that answer would be 0? One of the things that flux, if you think geometrically, what is flux telling us? And so if I just have a curve, not a closed curve, but just a curve, and I'm thinking about, say, like water flowing across it, and some of the water might be going faster, some of the water might be going slower, some of it might be going, my curve's here, but the water's kind of going sideways through it or something. And this flux integral is measuring, if the vector field is a velocity field, then the flux integral is measuring the amount of stuff that's passing through that curve, right? Directly through, right? So if it's going sideways through, it's only counting the perpendicular part of that motion. Okay? And so when I'm looking at this setup right here, thinking in terms of stuff passing through, down on the bottom side, stuff is generally passing into the circle, and on the top side, stuff is passing out of the circle. And by the symmetry of this whole setup, this is a very symmetric curve, it's a very symmetric vector field, and it looks to me like everything that's going in is also coming out. And so, yeah, an answer of 0 is probably not too surprising. And you might say, well, won't that always be the case, that the stuff going in is equal to the stuff going out if you got a closed curve like that? And the answer is no. No, it's not. Again, if you're thinking about a water flowing situation, you might have a drain in here, for instance, and some of the water that's going in never comes out because it goes down the drain. Or you might have a little spigot in there and there's water actually coming out of there, so you have you'd have a source. They're called sources and sinks. So it's possible that with a closed curve, you could have a flux being positive, meaning that you have a source inside and more is coming out that's going in, or you could have a flux that's negative, in which case there would be a sink. And we will discuss that in a video for the next section. Anyway, there's the basic integral of flux. It is just the integral of the normal component of a vector field across the curve. Enjoy.